Hello everyone, welcome to Chapter 4. This is the first video of Chapter 4. Now in Chapter 3 we talked about how to describe and control processes. So in Chapter 4 we're going to get into threads and what those mean, how they're different from processes, and how we can use them in programming and operating systems. Now this video will cover section 4.1 in your book, Processes and Threads, and we'll cover the distinction between the two, what makes a process, what makes a thread, and what makes them different. We'll talk about both single and multi-threaded approaches to programming and using threads. We'll talk about threads in a process, the benefits of a threaded approach, the execution states of threads, and what we need to do to keep our threads synchronized. Now let's recall from Chapter 3 that a process contains two specific characteristics. We have resource ownership, where a process includes a virtual address space to hold the process image. Now that process image, again, is a collection of the program, the data, stack, and attributes defined in the process control block. From time to time, that process may be allocated control of resources such as memory, I/O channels, I/O devices, and files. So the OS performs the protection function to prevent unwanted interference between processes with respect to those resources. Another characteristic of a process is the scheduling or execution. The process follows an execution path that might be interleaved with other processes. Now, from Chapter 3, this is where we took a look at the memory addresses that processes were accessing, and we have a dispatcher that can tell the process that, okay, you've timed out, so it's time to give another process an opportunity to run. That's where we have the interleaving. So a process has an execution state, running, ready, etc., and refer back to Chapter 3 to our 5-state process diagram for this, and a dispatching priority, and is scheduled and dispatched by the OS. Now, we'll use these same characteristics to talk about threads, but to distinguish between processes and threads, the unit of dispatching when we're dealing with threads is referred to as a thread or lightweight process. The unit of resource ownership is referred to as a process or task. And multi-threading is the ability of an operating system to support multiple concurrent paths of execution within a single process. So a single process can contain multiple threads. So let's talk about the single-threaded approach. The first thing to keep in mind is that the squiggly lines on the diagram indicate a single individual instruction trace. Now, with a single thread of execution per process, the concept of a thread basically isn't recognized. If we have one process, then we're only going to have one thread executing within that process. If we want to run multiple processes, each process will have only one thread, so we'll just need one process per instruction trace, per executing process. MS-DOS is an example of this approach in action. Let's contrast that with what we see on the right-hand side of this diagram, or multi-threaded approaches. Now, a Java runtime environment, as well as Windows, Solaris, many modern versions of Unix, among various others, are examples of operating systems that implement this kind of approach. So basically just what we have here is one process can have multiple threads of execution within that single process. Once again, if we have multiple processes, each of those multiple processes can have multiple threads of execution within each process. Now, in the next several slides, we'll talk about this more in detail and what we need to worry about when we actually include the idea of a thread in our operating system and what we need to do to manage those threads within the processes. So let's talk about threads within a process. Now, each thread has various things that are listed here, and you'll notice that most of these are pretty much the exact same thing as a full-blown process has as well. Each thread has an execution state, running, ready, etc. The saved thread context when not running, just as a process saves its context when it's not running, each individual thread has its own context that can be saved when it's not running, has its own execution stack, some per-thread static storage for local variables that are thread-specific, and this is one to pay a lot of attention to, though, access to the memory and resources of its process. Now, every single thread within a process has access to the memory and resources of the process that it's a part of. This figure shows the distinction between threads and processes from the point of view of process management. In a single-threaded process model, no distinct concept of a thread here, the representation of a process includes its PCB, process control block, and user address space, and it also contains the user and kernel stacks to manage the call and return behavior of the execution of the process. While the process is running, it controls the processor registers, and the contents of these registers are saved when the process is not running. In a multi-threaded environment, we still have a single PCB and a single user address space associated with the process, but now there are separate stacks for each thread, as well as a separate thread control block for each thread containing register values, priority, and other thread-related state information. Since all the threads of a process share the state and resources of that process, we end up getting several benefits by using threads rather than separate processes. Threads all reside in the same address space and have access to the same data. When one thread alters an item of data in memory, the other threads within that process see the results when they access that same item. If one thread opens a file with read privileges, other threads in the same process can also read from that file. So this leads to the benefits listed here. It takes less time to create a new thread in an existing process than to create a brand new process. It takes less time to terminate a thread in a process. It takes less time to switch between two threads within the same process than to switch between two completely separate processes. And so threads enhance the efficiency and communication between programs. In most OSs, communication between processes requires the intervention of the kernel to provide protection and the mechanisms needed for communication. However, because threads within the same process share memory and files, they can communicate with each other without actually having to go and invoke the kernel. So, if you have an application or a function that needs to be implemented as a set of related units of execution, it's quite a bit more efficient to do so as a collection of threads rather than creating separate processes. So, let's take a look at how we can use threads to our advantage on a single user system such as a desktop or a laptop. First of all, we can use threads to do foreground and background work in separate threads. A good example of this is a spreadsheet program. One thread could display menus and read user input, while another thread executes commands from the user and updates the spreadsheet. This arrangement can often increase the perceived speed of the application by allowing it to prompt for the next command before the previous command is completed. Another example of using threads to our advantage is in asynchronous processing. Asynchronous elements in a program can be implemented as threads. So, as a protection against power failure, for example, one can design a word processor to write its random access memory buffer to disk once every 60 seconds or so. A thread can be created whose sole job is periodic backup and that schedules itself directly with the operating system. There's no need for fancy code in the main program to provide for time checks or to coordinate input and output. A multi-threaded process can also increase our speed of execution by computing one batch of data while reading the next batch from a device. On a multiprocessor system, multiple threads from the same process could be able to execute simultaneously. So even though one thread might be blocked for an input-output operation to read that next batch of data, another thread could be executing. Finally, modular program structure could just be easier to design using threads. Programs involving a variety of activities or a variety of sources and destinations of I/O may be easier to design and implement using threads. This figure shows how multiple threads within multiple processes might be scheduled on a single processor. Thread A in process 1 starts out running. When it hits an I/O request, it stops running, it blocks, it goes into the blocked and waiting state, and thread B from process 1 takes over and runs until its time slice is expired. At that point, thread A from process 1 takes over again until its time quantum expires, but notice that thread C in a separate process, process 2, has been created in the meantime, so when thread A's time slice expires, thread C goes into the running state and things continue on from there. Some things to keep in mind about threads, though, is that in an operating system that supports threads, scheduling and dispatching is done on a thread basis. Most of the state information dealing with execution is maintained in thread-level data structures, but things to keep in mind is that suspending a process involves suspending all threads of the process. So in this figure, if we suspend process 1, both thread A and thread B will be suspended. And termination of a process terminates all of the threads contained in that process. So once again, if we terminate process 1, both threads A and thread B will be terminated as well. Finally, it's important to understand that we need to deal with synchronizing the activities of various threads. Because all the threads of a process share the same address space and other resources of the process, any alteration of a resource by one thread affects the other threads in the same process. This can cause various problems. For example, if two threads each try to add an element to a doubly linked list at the same time, an element might be lost or the list may end up malformed. There are various other issues and techniques to deal with them raised by the concepts of synchronization of threads, and they're for the most part the same as the synchronization of processes. We'll talk more about these issues and techniques in chapters 5 and 6. And that's it for section 1 of chapter 4. In our next video, we'll cover section 2 of chapter 4 on different types of threads.